Hello everyone. I am Professor Manish Mamtani from the Department of Geology and Geophysics, Indian Institute of Technology, Kharagpur in India. In the month of October 2016, an IUGS-TecTask Workshop entitled MOHR CIRCLE Simplified was organized by me in the Department of Geology and Geophysics, IIT Kharagpur in India. It was split into two parts. The first part, highlighting the philosophy behind the Mohr circle, was presented by me, and the second part, which was the more technical presentation, was made by my two former Ph.D. students, Tridib Mondal and Sivaji Lahiri. Recording of the first part of the workshop, entitled Mohr Circle the Philosophy, is available on YouTube, and the link for this is given here. Viewers are advised to look at the first part before going to the second part. This present recording deals with the second part of the workshop, Mohr Circle Simplified. The detailed presentations were made by Tridib Mondal and Sivaji Lahiri. The viewer is informed that Mohr Circle Simplified was one of the two workshops originally held in IIT Kharagpur in October 2016. The workshop manual is open access and can be freely downloaded from ResearchGate. The present recording has been done in September 2020 for the benefit of students and geology community as a response to increased online teaching due to the COVID-19 pandemic. In these 4 years, that is since 2016, a lot of research has been done by the present and former members of the Fabric Analysis Lab in the Department of Geology and Geophysics, IIT Kharagpur in India, as well as by other researchers in different parts of the world on various aspects related to the Mohr circle and its applications. However, the present lecture deals largely with the fundamental concepts and has been kept unaltered. That is, it remains in the original form as it was in the year 2016 when this particular workshop was organized. For the benefit of the interested viewer, I have included a slide at the end of this lecture which lists a few papers dealing with the Mohr circle and its applications post dating 2016 in order to keep the references more updated. This particular workshop, Mohr Circle Simplified, was split into three main components. The first component comprising introduction, basic concept of stress, Mohr Circle in 2D and its problems, Mohr Circle in 3D and its problems, and applications, was presented by Tridib Kumar Mondal. Tridib is presently an assistant professor in the Indian Statistical Institute, Kolkata. When this workshop was held in 2016, he was employed as a faculty in Jadavpur University in Kolkata, India. The second component of this particular workshop is scaling of the Mohr circle, and this is presented by Sivaji Lahiri, who completed his PhD under my supervision last year, and presently he is a postdoc in RWTH Aachen University, Germany. And finally, the third component of this presentation is made by Tridib Mandal once again, and this will be the summary. So from now onwards, for large number of slides, the first component will be presented by Tridib Kumar Mandal, and you will hear his voice in the presentation.
Now coming to the introduction part, it is very much important to understand the state of stress and its importance. Now when we talk about the state of stress, it is very much essential to know the force and deformation. So here we will introduce the MOHR circle. Now the question is, why to geoscientists? So in this lecture we'll try to find answer of these questions. Now there are some people who think that okay, this is too mathematical, there are lots of equations. Yes, there are some equations, but it is very much important to understand the physical significance of these mathematical equations. Now, coming to the basic concept of stress. The Mohr circle, as I was telling, that it's a graphical representation of any state of stress within the crust of Earth. So basically it is developed by German scientist Otto Mohr 1982, after whom the graphical method is now named. So it's a graphical representation of normal stress versus shear stress. Now coming to the force or pressure. So in the field we can't see the force or pressure. So what we can see the strain body. So strain, it defines any change of shape. It may incorporate volume or it may not incorporate volume. If it incorporates volume, then we call is a volumetric strain. So it's a basically change of relative position of particles in rocks in response to force. So force is the main culprit. So force is defined by any pull or push to a body or material. Now coming to the force, there are two types of forces. One is called body force and another is called surface force. So body force, it defines the three-dimensional forces. It affects every particle of rocks in a volume. Its magnitude is related to its mass. You can consider gravity, magnetic forces are the part of body force. Now coming to the surface force, it acts in the surface in the body. It results from the action of one body on another across a common surface. Now coming to the pressure and stress. So as you know, pressure or stress, both are almost similar and are defined by force per unit area. But to us, there are little bit differences between pressure and stress. Pressure is used for material with negligible shear stress, such as water or oil, whereas in case of stress, it is used for material with considerable shear stress, such as rock. So to understand the rock deformation, it is essential to understand the. Now coming to the unit of stresses, so normally we express stress as Pascal or bars or kilobars. Now there are two important terms. One is surface stress and there is stress at a point. Surface stress, it acts on the surface of the body and it is considered as first order tensor, while stress at a point, it's defined when the stress is acting at a point of the body and it is defined as a second order tensor. Now stress on a surface. Stress on a surface is a vector quantity and normally we express by the symbol called sigma and can be expressed as the ratio between force per unit area across which the force acts. In this figure, you can see that one force is acting on the plane. That dark shaded area you can consider as a plane, and the bold arrow, that inclined one, is the force is acting on this plane, And you can see it has two components. One is perpendicular to that shaded area. This is called the normal stress. And there are two other components which are parallel to the shaded plane. One is parallel to the x-axis and another is parallel to y-axis. These two are called the shear stress. So any force has two components. One is the normal stress component, another is the shear stress component. So normal stress and shear stress that can be expressed as a function of theta. Theta is the orientation of the plane on which force is acting. The normal stress, sigma n, is expressed by sigma cos square theta, while shear stress, sigma s, is expressed by sigma sine 2 theta by 2. So you can see here the force F is acting on the plane, and the inclined one in that figure is a fracture plane. So if we resolve the normal stress component and the shear stress component, and if we rearrange all these equations, we will get the normal stress sigma n and the shear stress sigma s as a function of cos theta and sin theta respectively. This slide shows the normal stress and shear stress, how it varies with the change of theta, that is the orientation of any plane or fracture plane on which the forces are acting. In the first figure, you can see the normal stress is maximum when theta is equal to 0 degree, because normal stress is a function of cos theta. And as we increase the theta, the sigma n value is decreasing. While in the second figure, you can see the shear stress is minimum when theta is equal to 0 degree, and it increases as theta increases and ultimately reaches its maximum when theta is equal to 45 degree, then again it decreases. Now there are some sign conventions, and it is very much important to understand the MOHR circle. So before going into the further details, we should know about the sign conventions. So in the structural point of view, we consider compressive stress as a positive, while extension we consider as negative, or tensile stress is negative. Anticlockwise rotation we consider the sinistral positive, and the dextral, the clockwise rotation, we consider is a negative. Now stress at a point. Stress at a point is expressed three-dimensionally. It is considered that stress components are acting on each surface of a very small cube. Each of the surface has normal stress and shear stress vector. Here, this is the very small cube placed in x1, x2, x3 coordinates, and you can see the normal stresses and shear stresses are plotted in each surface of the cube. For example, sigma 33 is a stress, normal stress, acting parallel to x3 axis while it's perpendicular to x1, x2 plane. In case of sigma 32 or sigma 31, both these two stresses are shear stresses. It is parallel to x1, x2 plane. Now, in case of sigma 32, that means this shear stress is acting the plane which is perpendicular to x3 axis and parallel to the x2 axis. Similarly, for sigma 31, this is the shear stress acting on a plane which is perpendicular to x3 axis but parallel to x1 axis. Similarly, for sigma 23, sigma 21, and sigma 13 and sigma 12 will be expressed. Therefore, By resolving all the normal stresses and shear stresses components that are acting on this very small cube, we can have these 9 stress vectors, and that can be represented by this stress matrix, normally represented by sigma ij. And the diagonal component of this matrix is the normal stress component, that is the sigma 11, sigma 22, and sigma 33. All other 6 components are considered as shear stress component. Now consider the situation where the cube rests at equilibrium. That means it doesn't suffer any rotation. So then in that case, we can write sigma 12 is equal to sigma 21, sigma 13 is equal to sigma 31, and sigma 23 is equal to sigma 32. So there are 6 independent components to the stress matrix, and it gives a symmetric stress matrix. Symmetric stress matrix where changing columns to row doesn't change anything. So again, this is the normal stress components. So coming to the principal stress, this is very much important. If the stress on a plane becomes perpendicular to the plane, the shear stress value will be 0. In such case, the stress matrix reduced to these components. So where you can write sigma 11, sigma 22, sigma 33, only diagonal axes are there, while other components, that means the shear stress components, are 0. So in the above matrix, sigma 1 or sigma 11, sigma 2 or sigma 22, and sigma 3 or sigma 33 are known as principal stress, where the sigma 1 greater than is equal to sigma 2 greater than is equal to sigma 3. The principal axes of stress are known as major, intermediate, and minor axis of an ellipse. This ellipse is known as stress ellipsoid. Now the stress at a point in a rock can be classified according to the shape of the stress ellipsoid. It could be triaxial stress, it could be biaxial stress, it could be uniaxial stress, or it could be hydrostatic stress. So in case of triaxial stress, so it's a state of stress in which all 3 principal axes are non-zero. That means sigma 1, sigma 2, and sigma 3 not equal to 0. In biaxial stress, where only 2 principal axes are non-zero while one will be 0. In uniaxial stress, where only one principal axis is non-zero while other 2 axes will be 0. In hydrostatic stress, so it is a state of stress where the stress ellipsoid is perfect sphere. That means sigma 1 is equal to sigma 2 is equal to sigma 3, and there is no shear stress component. Now, there is one more important term that is called mean stress. Mean stress is defined as average of the principal stress. In 2 dimension, it is sigma 1 plus sigma 2 by 2, and in 3 dimension, it is sigma 1 plus sigma 2 plus sigma 3 by 3. Mean stress is independent of any coordinate system, and in lithosphere, mean stress is equivalent to lithostatic pressure, where lithostatic pressure can be expressed by rho gh. Rho is the average density of the crust, h is the height of the crust, and g is the gravitational acceleration. After mean stress, there is another important term which is called deviatoric stress. If you see any stress tensor, that can be splitted into 2 symmetric matrices. If you see this equation, so first one, the first matrix is the total stress. So that can be written into the mean stress plus one part which is another symmetric matrices. This is called the deviatoric stress. So the mean stress plus deviatoric stress is equal to the total stress. Now, what is the physical significance of mean stress and deviatoric stress? We'll try to see from this cartoon diagram. Now, what happens if the mean stress increases? If mean stress increases, shape remain same but size changes. But if the deviatoric stress increases, then shape changes while size remains same. So the mean stress is considered as isotropic component of the stress, while the deviatoric stress is considered as anisotropic component of the stress. Now, the deviatoric stress is typically represents the tectonic stress component, while isotropic component corresponds to the lithostatic pressure. Commonly, the isotropic component is much larger than the deviatoric component. So far, we have seen what is the normal stress and shear stress, what's the mean stress and the deviatoric stress, and what are the physical significance of mean stress and deviatoric stress. Now we'll see one exercise, and this will essentially help us to clear the concept of normal stress and shear stress. So the exercise is given here, a cylindrical specimen of rock with 50 millimeter in diameter and 100 millimeter long is subjected to an axial compression force of 5 kilonewton, and we have to determine the normal stress and shear stress on a plane inclined at 30 degree to the radial direction, the maximum values of the shear stress, and the inclination of the planes on which the shear stress is equal to 1/2 of the maximum shear stress. Now let's look at the answer for the first one. So normal stress is equal to sigma cos square theta. This is known to us. So sigma force per unit area. So area we can determine from the given data, and we know the theta is 30 degree. So by converting all this unit, here we can get the sigma n is equal to 1913 kilopascal. Similarly, we can determine the shear stress sigma s, that is 1105 kilopascal. Now for the second part of the question, we have to determine the maximum shear stress. So maximum shear stress occur when theta is equal to 45 degree. Now if you put the theta is equal to 45 degree, we can get easily the value of shear stress maximum. Here we have received, that is 1275 kilopascal. And similarly for the second part, we have to determine the angle of inclination of the plane on which the shear stress is equal to 1/2 of the maximum shear stress. So we can write the equation as we have written in equation 3 here, and we can determine the value of theta. So after completing the basic concept of stresses, we will move towards the MOHR circle. So first we will try to learn MOHR circle in 2D, then will come MOHR circle in 3D. Now to start with, we have to know that the concept of stress can be extrapolated to understand the state of stress at a point in 3D by visualizing a stress ellipsoid. It is necessary to know the magnitude and orientation of all the normal stress and shear stress on every plane that includes that point. Mohs circle provide a graphical means of calculating normal and shear stresses and the orientation of a plane in rocks. Now there are certain points which are very important, and we have to note down. For a given state of stress, the shear stress and normal stresses acting on a specific plane through a point are plotted on the Mohs circle. The Mohs circle depicts the orientation as well as magnitude of the normal stress and shear stress during brittle failure. And number 3, it doesn't take into account the geographical reference frame but reflects the sense of motion, either dextral or sinistral, along a plane. And finally, it predicts the relationship between rock strength and state of stress under which the rock fractures. The magnitude of stress varies with the orientation and size of the area on which the force is acting, because the stress is defined by force per unit area. So to determine the equation of Mohr circle, there are certain assumptions. So what are these assumptions? The assumptions are the whole system has no relative movement. It is under equilibrium and there is no rotation or translation. Compression of the body is represented in the positive side, tension is taken as negative side, and state of stress is represented by principal stresses. Now, to get the equation of Mohs circle, we have to resolve the normal stresses and shear stresses acting on the plane. For example, here F1 and F3 are acting. So for this particular case, F3 is acting vertically, F1 is acting horizontally, and area is A given here. So that is the fracture plane or plane of concern. And if we consider this is a fracture plane, and if we consider the force F3 and F1 are acting perpendicularly and horizontally respectively, then we can have a number of normal stress component and the shear stress component that is given in this figure. So we have to consider the forces normal to the plane and forces parallel to the plane. And if we rearrange the normal forces and shear forces, and if we use simple trigonometry, finally we end up with these two equations marked with yellow color here, the normal stress sigma n and shear stress sigma s. The normal stress is represented here by sigma 1 plus sigma 3 by 2 plus sigma 3 minus sigma 1 minus sigma 3 cos 2 theta by 2 and shear stress sigma 1 minus sigma 3 sin 2 theta by 2. The important thing is that here also the normal stress and shear stress are the function of cos theta and sin theta respectively. Now if we look at the equations of normal stress and shear stress very closely, then we can see the normal stress and shear stress equations are equivalent to the equations of circle, where normal stress equations can be equivalent to x is equal to p plus r cos theta, whereas the shear stress equations can be equivalent to y is equal to r sin theta, where the r is the radius of the circle and the center of the circle on the horizontal axis would be at sigma 1 plus sigma 3 by 2, 0, and the radius is sigma 1 minus sigma 3 by 2. So therefore, the sigma 1 plus sigma 3 by 2, we know this is the mean stress. So in two dimensions, the center and the radius of the Mohs circle is represented by the mean stress and deviatoric stress component of the stress matrix respectively. Now if you see the change of normal stress and shear stress with the change of theta, so here we can see when the theta is equal to 0 degree, the normal stress is maximum, then again it will decrease as theta increases. Similarly, when we see the shear stress as a function of theta, then we can see that shear stress is minimum when theta is equal to 0 degree, because shear stress is a function of sin theta. Then as theta increases, shear stress increases and reaches maximum when theta is equal to 45 degree. So this is how the normal stress and shear stress increases or decreases with the increase of theta. That is the orientation of the fracture plane. So the orientation of the fracture plane or the plane on which the forces are acting, that is very much important. So now we'll see how to draw Mohs circle, or we'll see how a plane is represented in the Mohs circle or in the Mohs space. So consider that there is a inclined plane. Here it is represented through a bold black line, and sigma 1 maximum principal stress is acting vertically, and it's making theta angle with the pole to this fracture plane. Now we will try to plot this plane into this MOHR space. To start with, first consider two axes, the normal stress axis and shear stress axis. Generally, normal stress axes are plotted horizontally parallel to the x-axis, while shear stress axis is plotted parallel to the y-axis vertically. In 2D, if we consider that sigma 1 is maximum principal stress and sigma 3 is minimum principal stress, we can plot the sigma 1 and sigma 3, and we can also draw a circle through this sigma 1 and sigma 3. Earlier we have seen how the normal stress and shear stress can be represented through a circle. Now here in the real space, the angle between sigma 1 and pole to the fracture plane is theta. And here you can see that angle between sigma 1 and sigma 3 is 180 degree. But in the real space, the sigma 1 and the sigma 2 or with the sigma 3 for 3D, they are mutually perpendicular. That means the angle between sigma 1 and sigma 3 or sigma 1, sigma 2 or sigma 2, sigma 3 is 90 degree. But when all these principal stress will be plotted into the MOHR space, they will be doubled. So whatever angle we'll measure in the real space, that will be double in the MOHR space. So here in the real space, we can see the theta is measured from the sigma 1 to pole to this fracture plane. So here from the sigma 1, we can take 2 theta angle to plot the pole to the fracture plane. Now the red dot point here on the periphery is the pole to the fracture plane. So any point on the periphery is basically pole to the fracture plane. Now, if this is the case, then we can easily determine the normal stress component and the shear stress component for this fracture plane. Now we can have another 2 points here. And the first point is with similar shear stress but different normal stress component. But in the lower one, lower dot point on the periphery, red dot point is with similar shear stress and normal stress component, but here sense of shear is opposite to the previous one. So MOHR circle describes the normal and shear stress acting on the planes of possible orientation through a point in the rock. Now, what are the components of MOHR circle? Now, if you consider this is the MOHR circle, so the diameter, that is the sigma 1 minus sigma 3, would be the differential stress. That is the difference between the maximum principal stress and the minimum principal stress. And the center is sigma 1 plus sigma 3 by 2 on the normal stress axis. So this is the mean stress. While the radius, that is the sigma 1 minus sigma 3 by 2, would be the deviatoric stress component. So the mean stress component is the isotropic stress part and the deviatoric stress part is the anisotropic stress component. Now we'll see if we change the mean stress or if you increase the mean stress, what would be the position of MOHR circle. Mean stress, that means it is defined by center of the circle, that is sigma 1 plus sigma 3 by 2. So if we increase the mean stress, definitely it will move towards its right hand side. So it has great implications in understanding the stability of the rock. I will come shortly about this one. Now what happens if the deviatoric stress increases? Since the deviatoric stress is represented by the radius of the circle, so the radius of the circle will increase if we increase the deviatoric stress. Again, it has great implications if we talk about the stability of the material. Now what happens if fluid pressure increases? If fluid pressure increases, that means it essentially decreases the mean stress component. When the mean stress component decreases, that means the MOHR circle will shift towards its left hand side. So once it touches these two inclined line called the fracture envelope. Again, I will come on this very shortly. But if it touches the MOHR circle, then the shear fracture will form. Now, there are different types of stresses which are commonly used. So first one is the general tension. We can see the MOHR circle is in the negative side. And the second one is the uniaxial tension. You can see the one axis is 0 and you have one non-zero value that is in the negative side. And the third one is the general tension and compression. So it has the both compressive value and the tensional value, or it has the positive sigma 1 and the negative sigma 3. And the fourth one is the pure shear stress and the uniaxial compression, here just opposite to the uniaxial tension, and this is the general compression, the last one. Now we'll talk about the fracture and the failure criteria. It also known as the Coulomb fracture criteria. This criteria predict the state of stress at which a given rock under compression is at verge of failure, commonly described as being critically stressed. So the relation between shear stress and normal stress can be represented by angle of internal friction phi. So the sigma s, that is the shear stress, is equal to sigma n tan phi, where the tan phi is the coefficient of internal friction, again that is represented by mu. A fracture criteria describes the critical condition at which the rock fractures. The Coulomb fracture criteria can be interpreted as a straight line in the MOHR space, with mu representing the slope and phi is a slope angle. Here sigma s is equal to sigma n tan phi is equivalent to y is equal to mx. This is the equation of a straight line. Now the fracture only forms if the internal strength of the cohesion is exceeded. Therefore, the Coulomb fracture criteria or the complete Coulomb fracture criteria is the shear stress plus C, that is the cohesion, plus sigma n tan phi, or we can write C plus sigma n mu, because mu is equal to tan phi. So here it is the equivalent of the equation of straight line, that is the y is equal to mx plus c. So the c here is the shear stress along the surface at normal stress is equal to 0. C is known as the cohesive strength. Now tan phi is known as coefficient of internal friction. Mu again is the slope of the straight line. Now the cohesive strength C and angle of internal friction phi is the internal property of the rock. Therefore, it varies from one rock type to another. The difference between 2 theta at which the fracture forms and 90 degree gives the angle of internal friction phi. Here you can see the relation between angle of internal friction phi and the orientation of the fracture plane. So 2 theta is equal to 90 degree plus phi, or theta is equal to 45 degree plus phi by 2. Here we can see the various state of stresses and failure envelope. So it shows the relation between the MOHR circle, the position of MOHR circle, and the failure envelope. So first one, the MOHR circle is away from the failure line, that means it is stable. The second one, the MOHR circle just touched the failure envelope, it is a critical condition. And the third one, when the MOHR circle is already touched the failure envelope, this is the unstable condition. Now the question is how the failure envelope is drawn. After a series of tests, the point of failure are joined together to get the failure envelope of a particular material. Now this failure envelope, where it cuts or meets at the normal stress axis, the angle between this envelope and this normal stress is the phi, that is the angle of internal friction, and m is the slope of the line, that is the tan phi, and c is the intercept on the shear stress axis when the normal stress is 0, and the critical shear stress, that is sigma SC, marked here in green color, that is the shear stress required for failure or faulting. So the critical shear stress sigma SC is equal to mu sigma n plus C. So we have seen that the Coulomb fracture criteria predicts the critical state of stress needed to create the shear fracture. But that is on the compressive regime. But what about in the tensile regime? Does this failure criteria valid? The Coulomb fracture criteria does not predict the tensile fracture. Why? Because the Coulomb envelope relies on the angle of internal friction, which is physically meaningless for the tensile normal stress. Experiments suggest mode envelope in the tensile regime is shaped like a parabola. So to define that, we need more fracture criteria, that may be the Griffith criteria or von Mises criteria. So here I have given the Griffith criteria, the von Mises criteria, how it's look like, just to understand the different criteria. Now we see in the field often we can see the deep of the normal fault is much steeper than the reverse fault, and that can be explained through this MOHR circle. Let's say this is the normal fault, sigma 1 is acting vertically and it's making theta angle with the pole to this plane, and we can easily determine the deep of the normal fault is at an around 60 degree here for this particular case, and similarly we can get the deep of the reverse fault is around 30 degree. So far we have seen how the MOHR circle is plotted, or how the fracture plane or any plane is represented through MOHR circle. We have also seen the different fracture criteria and how it is predicted. Now we'll do one exercise. This will clear the idea about MOHR circle. For example, here we can see that in a given state of stress condition, sigma 1 is acting vertically and sigma 3 is acting horizontally, and sigma 1 is recorded as 100 megapascal and sigma 3 is 20 megapascal. And here the orientation of the plane, different planes are given, so we have to determine the normal stress and shear stress on the fault plane. So we know the value of sigma 1 and sigma 3. That means we can easily plot the position of sigma 1 and sigma 3 on the normal stress axis, and we can easily calculate the theta, that is the orientation of fracture plane. And if we have all this data, we can easily plot graphically the fracture plane, and from this graph we can determine the normal stress and shear stress values. Now we'll move to the MOHR circle in 3D. So when we talk about the MOHR circle in 3D, that means we will be working with three principal stress axes, that is sigma 1, sigma 2 and sigma 3, and definitely sigma 2, since this is the intermediate principal stress and will be plotted in between sigma 1 and sigma 3, and then in that case we'll have three circle. One will be through sigma 1, sigma 3. The second circle will be through sigma 1 and sigma 2, and the third circle will be through sigma 2 and sigma 3. So this is the sigma 1, sigma 3 circle, and this is the sigma 1, sigma 2 circle, and this is sigma 2, sigma 3 circle. Now, what happens if the magnitude of two principal axes are 0? That means the Mohr circle will shift towards left, and here you see the sigma 1 is equal to sigma 3 is equal to 0. So only one non-zero value is there, that is sigma 1. This condition is called the uniaxial compressive, and this is just opposite to the previous one. This is called the uniaxial tensile. So here sigma 1 and sigma 2 is equal to 0, one non-zero component, that is sigma 3, and that is in the negative side. So this is the condition of triaxial stress, the first one. The second one is the biaxial stress. So only sigma 2 and sigma 1 are non-zero values here. And first one here, this is the biaxial condition. The sigma 1 and sigma 3 have the non-zero value, while sigma 2 is 0. Sigma 1 is the positive side and sigma 3 is in the negative side. And the second figure, where the sigma 1 is equal to sigma 2 is equal to sigma 3, so all are equal, all the principal stresses are equal. This is the condition of hydrostatic. Here we can see the different state of stress and the corresponding matrix, from hydrostatic stress to uniaxial compression to uniaxial tension to axial compression, axial extension, and the triaxial stresses. Please note the matrix, how it's changing with the change of the state of stress condition. And this is the pure shear stress condition. This figure shows graphically the deviatoric stress, the total stress, and the mean stress in the Mohr space. And mathematically, the deviatoric stress can be defined through these equations. Now, this can also be defined through this set of equations. So ultimately, we are plotting, or we are calculating the total stress in terms of the isotropic stress condition, that is the mean stress component, and the anisotropic stress component, that is the deviatoric stress component. Now, if the fluid pressure increases, as I was telling earlier, that the mean stress will decrease and the Mohr circle will shift towards its left hand side. So that means the effective normal stress would be the total stress minus the fluid pressure. So this implies that the rock can be deformed under poor fluid pressure even if the differential stress remain constant, because it essentially moves the Mohr circle towards the left hand side, and if it touches the Mohr envelope, the material will fail. Both the shear fracture and tensile fractures can occur under the effect of fluid pressure. The shear fracture will form if the circle touches the Mohr envelope, and a tensile fracture forms if the envelope is reached in tensile field. The fluid pressure can create fractures even at very low differential stress. Now we'll see another exercise on this effective fluid pressure condition. In a given fault plane, the principal stress magnitudes sigma 1 and sigma 3 is given, that is 50 megapascal and 31 megapascal at 0 pore pressure. The angle between normal to the fault plane and sigma 1 is given, that is 70 degrees. We have to determine the normal stress and shear stress. The rock has pre-existing fractures and the angle of internal friction is 39 degrees. So the injection of water into the rock creates a pore fluid pressure of 27 megapascal. So we have to determine the position of new Mohr circle, because as we inject the pore pressure or the water into the system, it will create the pore pressure and ultimately it will try to reduce the mean stress. Now let's see the answer of this question. Here you can see the Mohr circle is plotted with the help of the normal stress and shear stress values, and the Mohr envelope or the failure envelope is also plotted with the help of angle of internal friction. It may be noted that the rock has pre-existing anisotropy or pre-existing fractures, that means here the equation is considered as 0. So when we inject the fluid pressure, 27 megapascal fluid pressure, that means the mean stress will reduce by 27 megapascal and ultimately it will shift towards the left hand side, and if it touches the failure envelope, the material will fail. And here we can see the new MOHR circle, the new circle has already touched the failure line. That means the fracture is already developed. So this is the position of the new MOHR circle. So this is all about the basics of the MOHR circle in 2D and 3D. Now we will see one application that has been applied on the Gadag belt, that is the volcano sedimentary assemblages of Archean greenstone belt, Dharwar Craton, South India, and we'll see how the vein is or the vein orientation data are used to plot the 3D MOHR circle, and ultimately how that helps to comment on the fluid pressure condition. The MOHR circle has been used to determine the magma pressure and fluid pressure condition during dike and vein emplacement respectively. The method to construct the 3D MOHR circle was developed first by Jolly and Sanderson in 1997 to examine the condition of stress and fluid pressure responsible for the opening of pre-existing fractures during dike. Now, what are the conditions for new fluid-induced fracture formation or the reactivation of earlier fracture? For that, fluid pressure should be greater than or equal to normal stress acting on the fracture plane. And this has been used earlier by Delaney et al. 1986, and he proposed one term, that is driving stress ratio, as a function of fluid pressure, and theta, that is the orientation of fractures. And subsequently that has been evolved and used by Jolly and Sanderson with the help of driving pressure ratio and the stress. This is the pictorial representation of lower hemispherical equilibrium projection of pole to veins or dike and 3D MOHR circle. You can see in the first case, when the fluid pressure is equivalent to minimum principal stress, that is sigma 3, no fracture orientations are susceptible for reactivation. But as the fluid pressure increases, the range of orientation of fractures that are susceptible for reactivation are increasing. And when PF greater than or equal to sigma 1, the maximum principal stress, all the fracture orientations are susceptible for reactivation. At low fluid pressure condition, fractures of a restricted range of orientations get reactivated or dilated. This is called the cluster distribution of poles to veins or fractures. And at high fluid pressure condition, fractures with wide range of orientations get reactivated or dilated. We get the Gardel distribution of pole to veins or fractures. Normally, if we get the cluster distribution of poles to veins or dike, we interpret following Jolly and Sanderson that fluid pressure is less than sigma 2, that is the intermediate principal stress, while we get the Gardel distribution of pole to veins or dike. Again following Jolly and Sanderson, we call the fluid pressure is greater than intermediate principal stress, that is sigma 2. Now look at an example from the Gadag belt as I was talking. Now we'll see how the vein orientation data are used to plot the 3D MOHR circle as well as fluid pressure condition. And these vein data are collected from the Gadag belt, which is a part of greenstone belt of Western Dharwar Craton of Southern Indian Shield. This is the northern part of the Chitradurga belt. So this is the lithological map of Gadag belt. So it's a province of gold mineralization of Archean age. and the mineralization age is found to be 2.52 billion years. And as I was talking, that hydrothermal activity took place in that region, and gold deposition are associated with this hydrothermal activity. So these are the types of quartz vein that are been recorded from that area. So these quartz veins are essentially determined as extensional quartz vein. Sometimes it forms a crisscross pattern. Sometimes you can see the prominent median line, and these are the orientation of veins that are found in that region, and these are the fracture orientation. The lower rows diagram is the fracture orientation. So out of 296 vein data, there are 120 vein of which we could measure strike deep direction. Therefore, we can plot the pole 2 of this vein in the lower hemisphere equal area projection. Here, red line indicates the mean vein orientation data, and from the distribution it is clear that it is girdle type distribution. That means the fluid pressure was greater than sigma 2. But we don't know how much it was greater than sigma 2. Let's have a look on this issue. So once we confirm that this distribution is girdle distribution, then following Jolly and Sanderson 1987, I can easily determine the position of the principal stresses and the range of orientation of fractures, that is theta. These essentially help us to determine the driving pressure ratio R' and the stress ratio phi. R' is varies from 0 to 1, and here R' is 0.97, that means very close to 1, which signifies high fluid pressure condition. But we don't know how much it was high. So to know that, we have to plot this data into 3D MOHR circle. So from this stress ratio, we can easily plot the relative position of sigma 1, sigma 2, and sigma 3, and the range of orientation of fractures, that is theta. And if we get this range of orientation of fractures theta, then we can determine the fluid pressure line joining the 2 theta and 2 theta 2. Now these are the range of orientation of fractures that are susceptible to reactivation and dilation at high fluid pressure condition. Now from this we can interpret that, okay, in that region the fluid pressure was very high. As a result, the fluid burst into the crust and the vein forms at various orientations. Now if you see, although this is a girdle type distribution, but at the southwest corner we can see a prominent cluster. So if you assume this is the cluster distribution, that means the fluid pressure was less than sigma 2. And again, following Jolly and Sanderson 1997, we can plot the relative position of principal stresses and the range of orientation of fractures theta, and subsequently we can calculate the R' and phi, that is the driving pressure ratio and stress ratio respectively. Here driving pressure ratio is 0.07, that means very close to 0, which essentially signifies low fluid pressure condition. But how low? To define that, we have to plot this data into 3D MOHR circle. And with using stress ratio, we can plot the relative position of sigma 1, sigma 2, and sigma 3, and we can define the fluid pressure line joining the 2 theta 1 and 2 theta 2. And these are the range of orientation of fractures that are susceptible for reactivation or dilation at low fluid pressure condition. So we interpret that in the Gadak region, the fluid pressure has been fluctuated from high fluid pressure to low fluid pressure, and this low fluid pressure condition, only northwest southwest oriented veins were susceptible for reactivation because the anisotropy lies in this direction. So this was a very brief idea about the application of the MOHR circle The details are given in Mondal and Mamtani 2013 Journal of Structural Geology paper. Now, here we have seen how the MOHR circle are used to define the fluid pressure condition, but this is the unscaled MOHR circle. The next step would be the scaled MOHR circle, and that part will be taken by Sivaji Lahiri.
Hello, myself Shivaji Lahiri. In the beginning, Professor Mamtani introduced me that I have done my PhD with him. So in this presentation, I am going to talk about scaling of the 3D MOHR circle. So I think just before that, Dr. Tridib Mondal has already introduced you about the MOHR circle and what is the relation of MOHR circle with the stress state, or in fact how the state of stress can be represented by MOHR circle. And at the end, he has introduced a technique of drawing 3D MOHR circle from uh, extensional vein orientation data. He has also given you an example from Gadak region of southern India, which is in western Dharwad Craton. He has tried to show you some nice photograph of extensional vein, and from the extensional vein he has tried to show you that how to draw 3D MOHR circle. Now in this part, or in my part, I am going to show you how we can estimate absolute differential stress from the 3D MOHR circle. So that is actually the part scaling of the MOHR circle is concerned about. So to scale 3D MOHR circle, we need to go for, or we need to follow 3 steps. So step 1 is estimating fluid pressure from fluid inclusion study. So I think we are all familiar with fluid inclusions. Fluid inclusions are very common in vein quartz. So what happens during the growth of the crystal within the liquid? Sometimes due to disequilibrium, fluid gets trapped within the crystal structure. Those are known as fluid inclusion. These fluid inclusions are very important in geology or in earth science because they can provide us information about pressure and temperature of the liquid when the crystal was growing. So from this fluid inclusion study, we can estimate fluid pressure. So the next step is approximation of the rock failure criteria using Wake and Brown 1980. I think one particular point is very familiar to all of us, that to propagate any fracture or to propagate any vein, so the vein or fracture should exceed the tensile strength of the rock mass. So to exceed the tensile strength of the rock mass, hence to scale the 3D MOHR circle, we need to estimate, or we need to approximate a rock failure criteria. Now here in this particular study, we have considered Wake and Brown failure criteria. So in the later slide, I will try to discuss why Wake Brown failure criteria, not any other failure criteria. So the third step is fine adjustment. So once all of these steps are done, then we can scale the 3D MOHR circle, or we can get the absolute values of principal stresses and also absolute values of differential stresses. In this particular slide, we'll be discussing little bit in details of the step 1, that is estimating fluid pressure from fluid inclusions and what is the effect on the stress state. So as we know, or already we have discussed, that we get fluid inclusions within vein quartz. So once there is fluid inclusions, from the fluid inclusions we can estimate fluid pressure. Now, what is the effect of fluid pressure within the system? That we need to consider while you are scaling 3D MOHR circle. Now, as we know that with increasing fluid pressure in any system, fluid pressure actually does not affect on the shear stress component, but fluid pressure affects on the normal stress, and it reduces the absolute value of the normal stress. So what happens if in a particular system fluid pressure continuously increases, then the MOHR circle shifts toward left. Now we need to consider this particular idea, or need to incorporate this idea while we are scaling 3D MOHR circle. So while we will be scaled 3D MOHR circle, whatever principal stresses we will get, those principal stresses will not be absolute principal stresses, that is sigma 1, sigma 2, sigma 2, sigma 3, but we will get sigma 1 dash, sigma 2 dash, sigma 3 dash. That is actually effective, maximum principal stress, that is sigma 1 dash. Sigma 2 dash is the effective intermediate principal stress, and the sigma 3 dash will be effective minimum principal stress. And the sigma 1 dash means actually sigma 1 minus PF. So this PF is because of the fluid pressure. Now in the next slide, we will be discussing about the second step, that is the consideration of Hoek and Brown failure criteria. Here we will discuss little bit in detail Hoek and Brown failure criteria. So the question is, why Hoek-Brown failure criteria, but why not Mohr-Coulomb failure criteria or Coulomb failure criteria? Now, Coulomb failure criteria is for homogeneous and isotropic rock, but when we try to understand growth of any fracture or vein, you always need to consider rock mass. Now, Hoek and Brown in 1980, they have proposed two expressions based on lots of experiment on different types of rocks. They have proposed a criteria which is known as actually Hoek and Brown failure criteria. So Hoek-Brown failure criteria is for rock mass. So it considers all sorts of anisotropy in the system. It considers weathering effect and all other things. So this is the reason why we have considered Hoek-Brown failure criteria for this study, because fracture or vein always develops within the rock mass, not purely isotropic and the homogeneous system. Now, after determining the Hoek and Brown failure criteria, or Hoek-Brown failure criteria, we need to know cohesive strength, friction angle, and tensile strength of the rock. That also we need to determine. And obviously, I have already mentioned that for considering the exact expression for Hoek-Brown failure criteria, we need to consider lithological variation and also differential weathering effect. Now, this is one expression that is being given by Hoek and Brown. Here you can see N and S. These are two constants, two empirical constants. And these two constants actually depends on the type of the rock and also weathering effect. Again, this is another expression. Here you can see I, J and K. These are empirical constant. And again, it depends on the type of weathering effect and the rock rheology. In this slide, we will be discussing about fine adjustment. What are the different points of fine adjustment and how we can perform fine adjustment and why it is important. Now, as we have already known that R dash and phi, that is the stress ratio and driving pressure ratio. So when we will be scaling 3D MOHR circle, we need to consider that R dash and phi should always remain constant and it should be maintained. Second point is poles of all veins should lie above the intrinsic rupture criteria. In our bachelor as well as masters, we have already learned that when MOHR circle touches the rupture criteria, we get fracture or vein. Now, in the natural system, we are already getting veins. Veins means these are already has got fractured, then fluid came within it. So the structural feature which we are already observing within the surface, those are already fractured. So if we try to plot pole to this fracture or pole to this vein, so this pole should touch the rupture criteria or it should lie above the rupture criteria. So that's why this second point is very critical for fine adjustment. Now third point is, as we already know that to open a fracture, fluid pressure should exceed the normal stress. If fluid pressure does not exceed, then we will never get veins. But in the surface, we are getting extensional vein. So we can obviously say that during the formation, fluid pressure must have exceeded, the normal stress. So we need to consider this particular criteria for our fine adjustment. So the normal stress corresponding to the reactivated fracture or normal stress corresponding to the obtained vein should lie above the rupture criterion. So these are the 3 points we should always remember for fine adjustment or to get the absolute value of differential stress. Here we will show in animation that how we can scale 3D MOHR circle, or in fact all of these 3 steps of scaling 3D MOHR circle, and ultimately how we will able to get absolute differential stress. So first, this will be our normal stress and shear stress axis. Once these are known, so we'll have to go for our determining Wake and Brown failure criteria. Once this failure criteria is known and these are plotted on the sigma n and the tau n space, the inter axis or the inter system will be all easily scaled. Already it will be scaled. So once these are done, so this will be our fluid pressure line, because as we have already discussed that with increasing fluid pressure, MOHR circle shifts toward left and the shifting will be equal to the amount of fluid pressure. So then obviously the fluid pressure line will come to the 0th position. So we already know theta 3. So once this theta 3 is known from the orientation of the veins, which is already discussed by Dr. Tridib Mondal. So this will be our angle 90 degree minus 2 theta 3. So we can draw a line here. Once this line is known, then we can draw a circle considering this radius. And again, from theta, from phi or from the stress ratio, we can easily determine the exact position of sigma 2 or sigma 2 dash. Once the sigma 2 dash value is known, so we can draw other two circle or other two planes. So this will be your sigma 3 dash position, this will be your sigma 2 dash position, and this will be your sigma 1 dash position. As I have already discussed, sigma 1 dash means this is actually sigma 1 minus PF. So PF is actually the fluid pressure. So if we add the fluid pressure with sigma 1 dash, then we'll get the absolute sigma 1 value. So once all of these things are done, then we need to go for fine adjustment. That is, the steps are already discussed in the last slide. So if these are known, fine adjustment is also done, then we can estimate absolute differential stress, sigma D. Now sigma D will be the difference between sigma 1 dash and sigma 3 dash. And obviously you can see sigma D is nothing but the diameter of the largest circle within the MOHR space. So in brief, I can say that in a particular region, if we are having extensional quartz vein, from this extensional quartz vein, we can develop 3D MOHR circle using Joly and Sanderson's idea. Once this MOHR circle has been constructed, then we can follow these steps, these 3 steps of scaling 3D MOHR circle, and finally we can ended up with finding sigma D value, that is the absolute differential stress.
Now we have come to the end of our presentation. So what we have seen the concept of stresses, basic concept of stresses, the normal stress and the shear stress, the mean stress, deviatoric stress, and what happens if mean stress increases, if deviatoric stress increases. So we have seen the anisotropic part of the stress, isotropic part of the stress. Then we have seen how to plot the fracture data or vein data or any plane data into the MOHR space. Then we have seen the state of stress condition, the failure envelope, and how to represent graphically. And we have also seen the MOHR circle in three-dimensional. Then we have seen how to plot this data and how to apply this data with giving some examples. So we have seen that it is very much important to understand physically the state of stress condition. Once that is clear, the physical significance of this diagram or of the equations, then it will be very easy to us. So thank you very much.
I hope that you have enjoyed the presentation on the MOHR circle that has been made by Tridib and Sivaji. Finally, some concluding remarks from my side. It was mentioned at the beginning of the presentation, whilst this TecTask workshop was held in IIT Kharagpur in October 2016, this recording has been done in September 2020. A lot of new work has been done since 2016. As promised in my introductory commentary, I am now including a final next slide listing some of the recent studies dealing with MOHR stress circle and its applications in structural geology. There are many more, but I am listing only those in which the present and former team members of Fabric Analysis Lab, IIT Kharagpur, were involved. I have been fortunate enough to have had a very active team of researchers in my Fabric Analysis Lab in IIT Kharagpur. There are many more members than what you see here. However, with specific focus on the MOHR stress circle and its applications in structural geology, these 5 researchers did a lot of work, and together we published large number of papers, mostly in the Journal of Structural Geology, Tectonophysics, and a few others. Uh, the present members in my team are continuing to pursue more applications of the Mohr stress circle and paleo stress analysis. And I hope that in the near future we will continue to exploit this particular tool very efficiently in the field of structural geology and tectonics. Thank you very much for your attention.